Alright, this constitutes the first part of the review for the third exam in Electrical Engineering 3342 for the spring. What I'm going to do here is I'm going to walk you through some example problems that are shown in the book so that you have a better idea of what we'll actually be looking at on the third exam. So this particular portion of the review will go for about 10-15 minutes, and then I'll stop the video and then we'll pick up with a second video. So first thing, let's go back and review a little bit about waveguides. So this example looks at a particular band rectangular waveguide. We're told that this is a K-band, KN band. The inner dimensions of an airfield KN band, and the KN band runs 12 to 18 gigahertz. It's known as WR62. It is a rectangular waveguide. It has dimension A of 1.58 and B of 0.79. We're asked to do several things. First of all, determine the cutoff frequency of the 5 lowest order modes that can propagate in the guide. Secondly, determine which modes propagate in the K alpha band. Thirdly, determine the phase velocity and guide wavelength for the TE10 mode at 15 gigahertz. And note that 15 gigahertz is right in the middle of the band. So the first thing we want to do is we want to address finding the cutoff frequencies of the 5 lowest order modes that will propagate in the guide. So in order to do that, we use the expression for the cutoff frequency, which is given here, and this is for a rectangular waveguide. M is the mode in the A direction and N is in the B direction, so it's the MN mode. C is the speed of light. So basically what you do here is you plug in the dimension for A and the dimension for B, and then we're just going to start plugging in ones, zeros, twos, and so on for the modes. So if you look here, if you plug in 1 for M and 0 for N, you get that the mode is 9.49 gigahertz. If you plug in for 2 for M and 0 for N, you get roughly 19 gigahertz. You get the same thing if you plug in 0 for M and 1 for N, and so on. So you can see what the mode distribution looks like for TE and TM. When you then look at which of these frequencies lies in the KN band, which is 12 to 18 gigahertz, you can see that only the TE10 mode lies in that band, or lies actually below the band. So it would be the only one here that would actually propagate. So for a TE10 mode in an airfield waveguide at 15 gigahertz, the first thing that we want to do is we want to look at the phase velocity. So for the phase velocity, we first look at the formula that relates the phase velocity to the cutoff in the guide, and notice the bar over the phase, meaning that it's the phase velocity in the guide. So we take C, which would actually be the phase velocity in air, and we divide by this waveguide factor, and what we come up with is 1.29 C, or 3.87 times 10 to the 8th. We can likewise use the formula for lambda to find lambda in the guide, and if we look at the waveguide factor here, 1.29 again, we can get basically what the new lambda will be. It'll be 2.58 centimeters. Okay, the next example that we want to do is to look at a C-band rectangular waveguide design. For the C-band rectangular waveguide design, basically our frequency range is 4 to 8 gigahertz for the C-band, and we have a rectangular waveguide such that the center frequency of the band is 6. And so what we want to do is we want that to be 25% higher than the cutoff frequency of the TE10 mode and 25% lower than the cutoff frequency of the next highest mode. So we're basically going to design the waveguide dimensions to meet these criteria. And of course the dominant mode that we want propagating is the TE10. Okay, so first of all, for the TE10 mode, if we take the speed of light and divide by 2a, that's going to give us the cutoff frequency. And we want that cutoff frequency to be 6 gigahertz. And then we want the dimension of the cavity to be such that our cutoff frequency the dimension is such that we'll be within 25% on the upper and lower bound. So basically, to find the lower bound, we want 1.25 times the cutoff frequency to be less than 6 gigahertz. So if we substitute in for the cutoff frequency, C over 2A, we plug that in and we're going to solve for A because we know what our desired cutoff frequency is. It's going to be 6 times 1.25 gigahertz. So we solve for the dimension A and we get 3.125 centimeters. Then for the TE20 mode, so that would be the next mode that would propagate, we want that to be 25% above the cutoff, or we want the cutoff to be basically for that mode, we want to be sure that we don't propagate that mode. So we basically take 0.75 times the cutoff frequency for the TE20 mode, and we're going to set that to be greater than or equal to 6 gigahertz. So if we look at that, we take 0.75 times C over A after we substitute in for FC20, and what we find out is that the upper bound for the dimension A is 3.75 centimeters. So we want A somewhere between 3.125 and 3.75, and if it lies here, then 6 gigahertz should be 25%, at least 25% above the cutoff, and then you'll be where the next mode, you're 25% below the cutoff for the next mode. So that's basically what this problem does. It designs the rectangular waveguide. Okay, so for the TE01 mode, we look at, so we're just wanting to make sure that that we don't have a problem with other modes. So we look at the TE01 mode. That gives you some dimension on the B, or some bound for the B direction. So using that second design criteria, now first of all, why are we using the second design criteria? We're using the second design criteria because, of course, B is greater than A. And so, I'm sorry, A is greater than B, so you already know that you're not going to cut off that TE10 mode, the dominant mode. So basically, what you want to be sure of is that you don't pass the higher order modes. So we take our 6 gigahertz then for the B dimension, and we set that less than or equal to 0.75 times the cutoff of 0.1. It's this N that gives you the guideline on what B can be. So that's why we go to our first mode that has a criteria on B. So for the 0.1 mode, we want 6 gigahertz to be less than or equal to 0.75 C over 2B. That ensures that we won't get the next mode at the 6 gigahertz frequency. So when we do that, we find an upper bound for the dimension B, and we find that B has to be less than or equal to 2.5 centimeters. Now, the design criteria don't set a lower band for the dimension B. The larger B becomes, the more power carrying capability you have. So you could look at the time average power for the TE10 mode and look to see that that's a function of A, and then when you find the time average power by substituting the Poynting vector in, you do get this, because you're integrating over dx dy, you do get this term that is proportional to B. So that may or may not have some bearing on your choice for design of B. It's just a consideration. The other consideration that we're not discussing in this example problem, but one to keep in mind, is that obviously the larger the dimension B, the larger the potential conductive losses.